Welcome back, folks. We're moving on to 2.9, linear inequalities. We're going to be graphing inequalities on a coordinate plane. Now, as it says, think about this. If you need at least 8 pizzas for a party and decide to buy some combination of cheese pizzas and pepperoni pizzas, what are some good pizza orders you can make and what are some bad orders? Alright, let's take a little look at that. Alright, let's make a graph of this. Okay, now we got my happy face over here and my sad face, so of course my happy face is going to be good orders. Alright, well, 8 pieces of graphs. Now, one very, very logical thing to do, I think, would be to make 4 cheese and 4 pepperoni pizzas. Alright, other things you could maybe do is maybe do 6 cheese, because maybe not so many people like pepperoni, and do 2. But I want to point out I've got at least 8 pizzas. So yeah, I could do stuff like switch it around to 2 and 6 now, but I could go crazy and maybe go something like 5, and I need at least 8, which means I can go bigger. So maybe instead of just going 3 here, maybe we go a little crazy and go with maybe 6. Or maybe we just go with 7, and then we go with maybe 8, or something like that. Alright, and we can do this all day. Alright, so let's plot those. I've got 4 cheese and 4 pepperoni, I'm about right there. I've got 6 cheese, 2 pepperoni, I'm there. If I flip it around to 2 and 6, I'm right there. But then I got crazy and I said 5 and 6, that puts me right there. And then 7 and 8 puts me right about there. Okay, so we have this kind of arrangement of stuff kind of all over. Let's go with bad cheese pepperoni. Okay, well, maybe I get my 4 cheese, but if I need 8 pizzas, maybe something bad would be like just 2. Or maybe I only get 1 cheese and 1 pepperoni, that's obviously bad. Or maybe even just 3 cheese and 2 pepperoni, that still doesn't make my 8. Or maybe I just am a really big jerk and make 0 and 0. Okay, or anything else you want to do that doesn't quite give us 8. So maybe we get close, maybe we get 5 and 2, so we're close but no cigar. Okay, now plotting our bad ones, I'm going to use little X's for this. So 4 and 2, that's bad. 1 and 1, also bad. 3 and 2, bad. 0 and 0 was bad. We got 5 and 2 was bad. Okay, you kind of see a little bit of stuff forming, but let's go a couple steps deeper. Alright, again, if I want at least 8, anything that adds up to 8 would have worked. So I could have gone with 0 and 8, I could have gone with 1 and 7. That one worked right there, we already had. Maybe 3 and 5 is good. And if you notice, you get this nice little diagonal line of kind of the edge of what does work. Now this is the minimum I could have got. Of course, I could have gone like 4 and 9 or something like that. Or I could have gone 8 and 3. I could have gone 9 and 5. I could have gone anything out here in this big area and everybody would have been happy. And on the flip side of that, okay, anything here that doesn't add up to 8, like 2 and 3 right there, no good. 1 and 5, no good. Notice anything that I'm picking down here, 4 and 1, bad. 3 and 0 is bad. So everything over here is bad and everything over here is good, and I've got this nice little line right here of good stuff as well. Okay, again, we could do this all day, but I'm sure you don't want to see me do that. Alright, so basically, a situation involving an inequality with 2 variables, again, at least is a phrase that implies an inequality, can be represented by a graph. Okay, and the graph's going to have 3 regions. The good points, okay, those are all those blue ones that we just had. The bad points, all those red ones we were just talking about. And what I'm going to term as the boundary line. Okay, the boundary line is basically the transition between the points that are good and the points that are bad. Okay, our job, as it says right here, is to show which of the points of the graph are good and which ones are bad. Alright, let's see how that's going to work. Alright, so let's go ahead and start graphing linear inequalities. We have my example here, y less than or equal to 3/5 x plus 1. Okay, first thing I want you to do is graph the boundary line. Okay, so what we're going to do is just imagine this thing without the less than or equal to sign and just a regular equal sign. So basically this you don't actually have to write out, but kind of what I want you to have at least in your head. Okay, just an equal sign for now because I'm graphing a line as it says. And I'm going to make a solid line here because of the or equal to bar. Okay, and what that means is that, as it says here, that the points on the line are actually going to be solutions to this. So let's see what that looks like. Plus 1 for my intercept right here, and then my slope is 3/5, so I'm going to go up 3 over 5, make a dot, and then again I can always go up 3 more and over 5 more. And since I've run out of room, I can go back to the left now, so down 3, left 5, and then down 3 more, left 5 again. Got my nice straight line, and again, because I have the or equal to bar, it means that all of these points are actually solutions if I plug them back in, and likewise any other point that's on this line. Now granted, the ones that we've plotted here are pretty much just the ones that have the nice whole numbers. All the other ones, like this guy, this guy, this guy, those guys are all like little decimals or fractions or however you want to think of it. But anyway, there you go. All those are solutions. That's why I made a solid line. Alright, now I'm going to shade the side of the line that works, and the way I'm going to do that is I'm going to pick a test point of some sort. I can pick any point that's on the graph that isn't one of the points on the line. Okay, I'll be honest, the one that I usually pick is the origin 0, 0, just because it's really, really nice. So I'm going to pick 0, 0. Okay, now I said it's really, really nice because when I'm plugging 0 in for things, it has a tendency to cancel stuff out. So here we go. I'm going to plug 0, 0 into y less than or equal to 3/5 x plus 1, just the original guy. So I've got 0 for y, less than or equal to 3/5 times 0 plus 1. Alright, and as I said, 3/5 times 0 is 0, so what I really have is 0 less than or equal to, well, the 0 cancels out, so I'm not going to bother writing it, but I'm going to write this 1. Okay, is 0 less than or equal to 1? Well, absolutely it is. Yay! Okay, so what that means for us is that this point works, but what it also means, just kind of like the pizza example, notice again I've got my boundary, and this point works, and every other point that's over here on this side of the line is going to work as well. So what we're going to do for this, and I apologize, this is not going to look very good on the computer, but what we're going to do is shade in that side of the line, showing that every single point over here will work. Okay, I'm sure you don't want to see me do this in the video, but if we pick any point out here at all, I could pick this one, I could pick this one right here, I could pick this one over here, I could pick that one right there. Any point I pick, if I plug it into the original, it works. Likewise, if I pick any point out here in the kind of upper left part of our graph, it will not work at all and give me a false statement. But basically, that's what your answer is going to look like. Alright, let's do another one here. Hopefully that'll help clear things up in case it wasn't clear from the last one. Alright, again, step 1, I'm going to graph my boundary line. So again, I'm imagining y equals 3x minus 4. So again, my negative 4 is my intercept, so I put down there my first dot. And again, for those of you who like doing it, think of it as 3 over 1. So I can go up 3 over 1, and then I go up 3 more over 1, and I do that until I've covered a pretty reasonable amount of graph. And then, of course, I can take it in the other direction. Okay, now, I haven't drawn a line yet, and right over here, we're going to make a dotted line if your inequality symbol does not have the or equal to line. Alright, so basically, on the last one, if I picked one of these points and plugged it in, I got something that works. Now let's pick one of these other ones, like this guy right here looks like the point 3, 5. So he's 3, 5. I'm going to pick him and plug him in this guy again. So if I plug in 3, 5, okay, the 5 is my y. I've got greater than now 3 times 3 minus 4. And I apologize for cramming this in here, but this gives me 5 greater than, well, 3 times 3 is 9, and 9 minus 4 is 5. Well, is 5 greater than 5? Well, certainly not. Okay, so I'm going to use a dotted line now to show that this point isn't a solution, nor is any other of these points. So this dotted line says that my boundary is not part of the solution, but what's about to happen when we do the other shading is that one side or the other is going to have a whole bunch of points that are solutions. But unlike the pizza problem, the ones on the line here are no good. Alright, so now we're going to shade the side of the line that works, pardon me on that. Okay, again, I'm going to pick the origin just because I honestly can, and it's easy to plug in 0, 0, but again, I could pick any point on the graph, it's just the origin is very convenient. So picking 0, 0, alright, again, I plug in 0 for y, and I then get a greater than 3 times the x, which again is 0, and then minus 4, and then I work this out and see if it's true. So 0 greater than 3 times 0 is 0, minus 4, and again that just gives me 0 greater than negative 4. Okay, this is also a true statement. And again, so that means the origin is this nice happy point that works, and all of his friends over on this side of the line as well. So again, what I can do there is shade over there, and there's all my answers. Any point I pick over here is going to work. Any point I pick over in the kind of lower right part is not going to work. Alright, well, of course, there's always a danger that your inequality is not written in your slope-intercept form, so of course we need to get it there if it's not. So, subtract your 4x from both sides here. Okay, we've done this 1,000 times. 3y greater than or equal to negative 4x plus 15. Okay, again, just treat this like an equal sign, basically. Dividing by 3. And now I've got y greater than or equal to negative 4/3, because that doesn't reduce, but then the 15 over 3 does reduce down to a 5. Alright, so again, I'm going to graph my boundary line, so I'm imagining that I have an equal sign here. So I go up 5 for my intercept, and I go down 4, and to the right 3. And again, I just do that a few times. 4, 1, 2, 3. Okay, and again, I've got a little bit of space, so I'm going to take it the other direction. Okay, now again, I've got the or equal to bar here, so it lets me know that I'm going to do a solid line. Right. So, I draw my line through there, nice and solid, again indicating that the points that I'm just drawing right there are all solutions if I plug them back into the original. And then again, I want to pick a point, and I'm going to pick the origin again just because it's available. And I've got 0, 0 that I'm checking, so what that gives me is 4 times 0 plus 3 times 0 greater than or equal to 15. Okay, now I love actually having this form for the equation because everything on this side is a 0, so everything cancels out down to a 0. And I get 0 greater than or equal to 15. Well, that is certainly not true. So again, origin right here, big frowny face, doesn't work. But that means all these guys on this side are bad, and then all these guys on this side are good. So there's my solution. Alright, now as it says here, be careful when dividing by negatives. Okay, now remember there's some fancy rule about negatives and inequalities. So as I start doing this guy, I subtract my 5x from both sides. Okay, now nothing weird about subtracting ever. But I've got negative 2y greater than negative 5x plus 8. But now I'm dividing by a negative 2. I'm going to put that in a fancy red so it stands out a little bit. Okay, again, big red flag. When I divide by a negative 2, it means something very, very special. I do get a y, I do get a positive 5 over 2x, and then I do get a negative 4 right here. But remember, since I divided by a negative, my inequality sign has got to flip around in the other direction. So this greater than sign flips around to become a less than sign. Okay, very, very important here, especially because it's going to dictate where I shade. And if my inequality is facing the wrong way, I'm going to shade the wrong way. But here we go. Down 4, up 1, 2, 3, 4, 5 over 2. And then I'll do that a couple times. Ran out of room, it looks like, so now I'll go down 5 over 2 the other direction. Okay. And then again, since I don't have the or equal to bar, I'm going to use a dotted line in this case. Again, I'm indicating that the points on this line are not solutions to the original inequality. Okay, and then now I'm at the pick a point phase. And again, I'll pick 0, 0, okay, because it's not on the line. Again, that's the determination whether you can pick it or not. And so now I've got 5 times 0 minus 2 times 0 greater than 8. And again, this is awesome because the arrow cancels to a 0, and I'm left with 0 greater than 8. So in this case, again, the origin is kind of sad about things because he doesn't work. So everybody over here on kind of the upper left half is bad, and which means that everybody over here on the lower right part is good. And there's the solution for that guy. You may have been thinking, hey, what about those weird cases, those unusual ones? And, well, here they are. Alright, so I've got y less than 2. Again, it's unusual because these are my horizontal and vertical lines, and hopefully what you remember is that the y equals variety is the horizontal. Alright, so again, I'm really considering graphing y equals 2. So I go to 2, and I imagine my nice horizontal line going through here. Okay, I'm not going to put all the points. The other thing is, notice that I don't have the or equal to bar, so that lets me know that in this particular case, I'm graphing a dotted line. So there you go. Okay, now maybe what's a little bit weird about this is now as I pick my point to test, and again I'll use the origin because my line doesn't pass through the origin, 0, 0. Okay, now I've got a y, well 0 is y, so I put a y there, a 0 there, and I've got a less than 2, and then maybe somebody starts freaking out because you never put the x anywhere. Well, that's okay because there was no x here, so you just don't plug it in. And then just ask yourself, hey, is 0 less than 2? Well, it certainly is. So, again, that means that the origin right here is just completely happy because he worked, and again, what that means is all his buddies on this side of the line, kind of the lower half of the graph, they all work. So there's what this guy's solution would look like. Okay, as we move over here to x greater than or equal to 2, again, he's going to be a vertical line at 2. Again, I can put a couple more points here. But as I have the or equal to bar, again, what that means for us is we're going to have a solid line instead of dotted. So I draw my best solid line here. Okay. Again, I'm going to test myself at 0, 0, and see if I get a true or false statement. Okay, again, x, well, that's 0, so I plug in a 0 for x. I have my symbol, and then I have my 2, and just like the last one, I just didn't have the other letter to plug in, so I didn't bother. Is 0 greater than or equal to 2? Well, no. Alright, it's not greater than or equal to 2, so in this case the origin is a little bit sad. Alright, but what that means is I don't shade over here on the left, and what I end up doing is shading over on the right side instead. Okay, so that's basically what those two unusual cases will look like. Alright, so here's a couple to try on your own. Of course, if you have any questions, make sure you ask me in class. See you then.